It has been over a year since the Vikram Lander successfully touched down on the lunar surface, capturing the hearts of millions around the world. Although both the Vikram Lander and the Pragyan Rover have grown old resting on the moon's soil, the joyful memories and accomplishments from their mission remain vivid in our minds. For much of the past century, the United States and Russia were the undisputed leaders in the field of space exploration, making remarkable advancements and achieving historic milestones. However, India has emerged as a formidable competitor, showcasing its prowess in space technologies. ISRO, Indian Space Research Organization, has been relentless in its pursuit of excellence, launching a series of space missions that have continually filled the nation with pride. Most recently, with the launch of the Spadex mission, India is set to demonstrate its capabilities in a crucial area of space technology. This ongoing mission signifies not only a technical achievement, but also India's commitment to advancing its role in global space exploration. As we look forward to future developments, the journey of Indian space missions continues to inspire and ignite excitement across the country and beyond. The Spadex spacecraft are currently orbiting the Earth at an altitude of 470 kilometers. One of the key operations they will perform is the docking and undocking process, which is crucial for the success of Gaganyaan, Chandrayaan-4, and other larger space missions. The Chandrayaan-4 mission aims to collect valuable samples from the surface of the moon and return them to Earth for analysis. In this video, we will delve into the details of the docking mechanism and how it works using step-by-step 3D visualizations. Before that, we will provide an overview of the Vikram Lander and the Pragyan Rover, highlighting their scientific experiments and objectives on the lunar surface. These experiments are designed to enhance our understanding of the moon's geology, composition, and potential resources, paving the way for future exploration. ISRO made the strategic decision to land the Vikram Lander near the South Pole, approximately 600 kilometers away from the moon's south pole. This historic landing point has been named Shiv Shakti Point, with coordinates at 69.3 degrees south and 32.3 degrees east. Notably, this site is located on the near side of the moon, the side visible from Earth, rather than the far side, which has seen only one human visit. While extensive exploration has taken place on the near side of the moon, the South Pole presents a unique challenge for landings due to its rugged terrain, characterized by deep craters and towering mountains. The moon's axial tilt also contributes to the extreme conditions experienced in this region. During the lunar day, the sun remains at the horizon, and at night, temperatures drop to -230 degrees Celsius. These harsh conditions pose a significant risk to the electronic devices on board the lander and rover. Given these constraints, any planned scientific experiments must be completed within a limited time frame of 14 Earth days, corresponding to a single lunar day. Both the Vikram Lander and the Pragyan Rover were designed to operate effectively during this period, ensuring they maximize their contributions to lunar research during their brief but critical mission. Let's explore the significant achievements of the Vikram Lander on the moon. The Vikram Lander is equipped with 4 sophisticated payloads that enhance its scientific capabilities. 1. Chased payload. Known as Chandra's Surface Thermophysical Experiment, this mission aimed to measure the thermal characteristics of the moon's surface. The experiment employs a specialized probe capable of delving up to 10 centimeters beneath the lunar surface. The probe, equipped with a network of 10 finely tuned sensors, meticulously collected temperature data from various depths. Initial measurements recorded a remarkable decrease of 10 degrees Celsius for every centimeter beneath the surface. While the surface temperature reached a scorching 60 degrees Celsius under the harsh lunar sunlight, it dramatically dropped to -10 at a depth of 10 centimeters. This extreme thermal insulation reveals valuable insights into the moon's subsurface environment. RAMBA. The radioanatomy of moon-bound hypersensitive ionosphere and atmosphere payload focuses on studying the moon's extremely thin atmosphere, also known as the exosphere. Ramba applied a small current using a 5 centimeters metallic probe to measure plasma density near the lunar south pole. It confirmed a layer of charged plasma with electron densities ranging from 5 to 30 million per cubic meter, fluctuating with sunlight exposure. These findings are critical for lunar communication systems, enabling clearer signals with minimal delay. This knowledge aids future lunar exploration and supports plans for human habitation. ELSA, Instrument for Lunar Seismic Activity. ELSA is a cutting-edge device designed to monitor seismic vibrations on the moon's surface using advanced micro-electromechanical systems, MEMS. A remarkable recording was made when it detected vibrations caused by the Pragyan Rover's tire movements, offering data on lunar surface conditions. On August 26, 2023, just 3 days after Chandrayaan-3's landing, ELSA detected a potential moonquake. This marked the first seismic event detected on the moon in over 50 years. Scientists are analyzing the event to uncover the moon's geological processes, including its internal structure and evolution. 4. Laser Reflector Array. This payload, supplied by NASA, is mounted on the Vikram Lander to enhance distance measurement precision. By reflecting laser beams from the orbiter, scientists calculated exact distances between the lander and the orbiter. This technology improves landing accuracy for future missions and aids in the success of sample return and manned lunar expeditions. Pragyan Rover's payload rover carried 2 advanced scientific instruments. 1. Laser-Induced Breakdown Spectrometer, LIB. LIBS confirmed the presence of sulfur in the lunar soil near the South Pole, along with other elements such as aluminum, calcium, iron, chromium, titanium, and silicon. LIBS uses high-energy laser pulses to create localized plasma on lunar rocks. Analyzing emitted light reveals the elemental composition, significantly enriching our understanding of the moon's resources. APXS analyzed soil and rock samples on the moon to detect elements like sulfur, aluminum, silicon, calcium, and iron. APXS uses radioactive sources to emit particles and X-rays that interact with the atoms in the sample. This unique method allows highly accurate detection of elements and their relative abundance. These particles and X-rays interact with the atoms in the sample, causing the atoms to emit characteristic X-ray lines unique to the elements present in the material. By measuring the energies and intensities of these characteristic X-rays, the APXS instrument can identify the elements in the sample and determine their relative abundances with high accuracy. The rover traveled within a 500-meter radius of the Vikram Lander at a cautious speed of 1 centimeters per second, covering only 36 meters per hour. This deliberate pace ensured careful navigation of the moon's uneven terrain. On August 27, 2023, the Pragyan rover encountered a 4-meter-wide crater just 3 meters ahead. The mission team promptly commanded the rover to retrace its path, safely navigating a new route. Its navigation cameras and real-time monitoring ensured the rover continued its exploration safely. The Hop Experiment. 2 days before going into sleep mode, the Vikram Lander performed an unexpected hop experiment on the lunar surface. The lander's engines fired, lifting it approximately 40 centimeters above the moon's surface before descending and landing 30 to 40 centimeters away from its original position. This hop showcased the lander's ability to take off from the moon, an essential capability for future sample return missions. This achievement exceeded mission goals and opened doors for more advanced lunar exploration. Tashdam Propulsion Module and Shape Payload. The propulsion module not only carried the lander rover configuration to the moon's orbit, but also carried the SHAPE payload, spectropolarimetry of habitable planet Earth, From lunar orbit, SHAPE conducted spectral and polarimetric measurements of Earth, offering valuable data on atmospheric composition, habitability markers, and cloud dynamics. These insights may contribute to the search for habitable exoplanets. Spadex space docking experiment mission involves two small satellites, SDX-01 Chaser and SDX-02 Target. Each spacecraft weighs approximately 220 kilograms and will be launched by the PSLV C-60 into a 470-kilometer circular orbit at a 55 degrees inclination. The mission features a local time cycle of about 66 days. At launch, the PSLV's demonstrated precision will ensure a slight relative velocity between the Target and Chaser spacecraft as they separate from the launch vehicle. This incremental velocity will allow the Target spacecraft to drift to a separation of 10 to 20 kilometers from the Chaser within a day. Once this separation is achieved, the Target spacecraft's propulsion system will execute a drift arrest maneuver to neutralize the relative velocity. Following the drift arrest, the two spacecraft will share the same orbit and velocity with a separation of about 20 kilometers, a phase referred to as far rendezvous. Using a series of carefully controlled maneuvers, the Chaser will incrementally approach the Target by compensating for small relative velocities. These maneuvers will reduce the intersatellite distance progressively to 5 kilometers, 1.5 kilometers, 500 meters, 225 meters, 15 meters, and finally 3 meters, culminating in the docking of the two spacecraft. Upon successful docking, the mission will demonstrate the transfer of electrical power between the two satellites. After this, the satellites will undock and separate to commence the operation of their respective payloads, with an expected mission life of up to 2 years. In the future, Chandrayaan-4 mission, docking will be a key feature. The Vikram Lander, after collecting samples from the lunar surface, will fire its engines to ascend and rendezvous with a spacecraft orbiting the moon. This orbiting spacecraft will be waiting to transport the collected samples back to Earth. Once the Vikram Lander docks with the spacecraft will carry the lunar samples to Earth for further analysis in India. This concept outlines the advanced goals for Chandrayaan-4 and its integration with the Spadex mission, space docking experiment, demonstrating India's growing capabilities in space exploration and sample return missions. If you found this information insightful and believe it can inspire the next generation, I kindly ask for your support. Creating this 3D video was a labor of love, requiring over a year of dedication, countless hours of hard work, and significant financial sacrifices. I worked alone with limited resources, using a mid-range computer, which I bought with borrowed money, to bring this project to life. Your contributions, even as small as 2 rupees, can enable me to continue creating educational content. My UPI ID and QR code are displayed on the screen, and my bank details are in the description. Thank you for your support, and don't forget to like, share, and subscribe to help spread the knowledge.